Good evening, everyone, and welcome to the Amateur Radio Technician class, session number 10. During our previous session, we had a look at our Q&A, our curriculum progress. We also mentioned again our practice exams. Then we got into the technical topics of antennas. We dealt with resonance. We looked at half-wave dipoles, quarter-wave verticals, antenna calculations, beam antennas. We had a look at the isotropic, talked about antenna gain, Yagi antennas, rubber duck antennas. We discussed what the shielding effect was. We also went into some other antennas such as the 5/8 wave antennas. We discussed feed lines, and then we ended with our usual question pool review. Our agenda for this evening, we have a Q&A, a couple of questions to deal with. We have a look at where we are in the curriculum. We'll mention again the practice exams. Then we get into our technical topics for this evening. Standing wave ratio, or SWR. We'll deal with SWR meters, RF power meters. We'll discuss what are antenna analyzers, and then some components of amateur radio, antenna tuners, dummy loads. Then we'll go into some discussion on the various modulation types, AM, FM, PM. We will touch on what repeaters are again just quickly. Then we go into single sideband. We'll have a discussion on bandwidth. We'll talk about what is fast scan TV. We then discuss CW or Morse code. And then we'll begin or touch a bit on digital modes. Then we'll go into our question pool review and then set the date for the next session. So let's deal with a couple of questions from the last session that students had asked and we had not the opportunity to deal with. So let's go. First question is, very good one. What is the purpose of the J-pole antenna? So on your screen, you have what the J-pole antenna looks like. So if you look at it, you'll see that it's a fairly compact design. It's not a very large, wide antenna with a lot of components. So it's pretty compact. And because of that, it's also very easy to construct. So construction is quite simple for the average amateur radio operator. And of course, it also does pretty good in terms of bandwidth coverage across the frequencies that amateur radios will use. So whether it's cut for the 2-meter band or the 70-centimeter band, it covers the particular band quite well. So good wideband coverage. And of course, it's an omnidirectional antenna, meaning that it radiates 360. That means in all directions. And it tends to also have relatively low noise levels compared to some of the other vertical types of antennas. So very good question as to the purpose of a J-pole antenna. All right, next question is, and this was also a very good question, would window tint affect the signal as well? And we were talking about the shielding effect. You know, we had a nice picture of a car and said that if your radio is inside of the car with the antenna, you know, that shielding effect will attenuate or reduce your signal significantly. So the participant asked about tint. So that is, again, excellent question. And the simple answer is yes, window tint can potentially affect the radio signals, right? Now, it really depends on the composition of the particular tint. Tint itself is made of polyester film and it's treated with various coatings. Some of those coatings may have metallic content, you know, conductors or metals, right, in the film. So if it does contain metallic content, yes, definitely the tint can act as a barrier to the radio waves, further attenuating that signal, right? So yes, very good question. Potentially, yes. Really depends on the type of tint and the composition of that tint. Okay, so let's have a quick look at our curriculum progress. So this is where we are in respect of our course at the moment, right? So we have still a little ways to go, but we have made very good progress and covered a lot of material. Just a reminder to all participants, never too early to take practice exams to see where you are. These are the links that you can use to generate your own practice tests and see how you're doing. Take the opportunity to congratulate all students who have since taken exams and passed, and some have become licensed hams, gotten their US call sign, and some even the TNT call sign. Very, very great for the feedback when you have done your exams, and congratulations to all. All right, so just a reminder of the text that we're using, the No Nonsense Guide. So let's go straight into some of the technical topics for this evening. So we need to deal with SWR, standing wave ratio, and we remind ourselves that we keep saying that hams are matchmakers, right? So as we go through the course, we will further understand why we make that claim or that comment that hams are matchmakers. So on your screen is a definition of what standing wave ratio is about. It gives a lot of detail. So of course, this is not all necessarily on your exam, but I'll leave it to the participants. You get this slide deck so you can read this through. But we just mentioned that standing wave ratio, abbreviated as SWR, it's a measurement and it tells us how well our antenna, remember we are as hams looking to use our transceiver or transmitter to transmit into an antenna. So it is saying how well that antenna is matched to the radio's output as well as the transmission line that we use. So we'll get a little more into that using a diagram, but the rest of it here is for your reading pleasure. It gives you a bit of further information about SWR, and we highly encourage all participants to take a read of it when you get the slides from the slide deck. Please read it through. It should give you further and better particulars to help in the understanding of SWR. So next slide up. Right. So of course, if we were to look at our screen, we will see a diagram that shows our transceiver or transmitter or our radio. This is our radio. And then we have on the other end our antenna. And of course, what connects our antenna to the transmitter is our transmission line or feed line. And when we transmit on our radio, we send a wave down the transmission line to the antenna. That's exactly what we're trying to achieve. We want maximum transfer. We want maximum efficiency. Our radio signal, when we transmit, we want it all to go to the antenna, and then we want it to wirelessly leave the antenna and go into the air. And we want another amateur radio operator to pick up our signal. So that's what we're trying to do. So we want maximum transfer. But if our antenna and our transmission line, the impedance is not ideally matched, what we can do, we can have losses inside of there. And not all of the signal will be radiated as efficiently as we would like, right? Some of it will be lost as heat and so on, right? And of course, worse yet, if your SWR is poorly matched, on the transmitter end, I mean, that can generate a lot of heat inside of there due to detuning of the transmitter. So you don't want to do that. That could damage the final output transmitter, the transistors, what we call the power amplifier stage of your transceiver. So those components, while they're quite robust, you don't want to stress them out by heating them up too much. So you want to match your transmitter or your transceiver to your antenna and transmission line. And how do you know whether it's matched? Well, it's that magical term, standing wave ratio. And it really is a ratio of the transmitted wave or signal to the reflected wave. So when you transmit to your antenna, there will be a reflected wave, and that could be overwhelming and cause your antenna system to be not as efficient if it's not properly matched, if the impedances are not matched. So we have a little graph here that shows, the impedance, the SWR of the particular antenna that you're dealing with, and we're looking for a low SWR. So low SWR is good. And we'll show a screen just now of a meter that is reading this thing called SWR. So you'll see what a good SWR reading is. And when your SWR is as good as it can be, you have maximum power transfer. So that's why as hams, we are matchmakers, and we are always trying to match the antenna system to the transmission line. As we've gone into the course, a lot more of this will become clear, but just bear in mind, you want a good SWR, you want a good match. All right, so these are some meters here, right? These are actually SWR meters, screenshots of them. And on one side, we have a good SWR, and on one side, we have a not so good SWR, right? Or higher SWR. So let's try and read our meters. So these are meters that are placed between the transceiver and the antenna, right? To read this SWR. Remember, we say SWR is a ratio between the wave that goes out to the antenna and the one that is reflected back. So if we were to look at the left-hand side, this instrument here, if you read the forward scale here, you see you have a pretty good transmit output power here. That's the needle here showing us this is what we're transmitting. Maybe we're about 11 and so 11 and a half watts or so forward, maybe, right? And you'll notice the reflected scale. That dial's hardly moved at all. It's just a little, what do you call it? Right? Just a slight movement. So it's intersecting here, and at the intersection, we can read out our ratio, and we'll see that the SWR, according to this, is 1.2 to 1. And we did say SWR is a ratio, right? So 1.2 to 1 is pretty low. It's pretty good. I mean, you're trying to get as low as possible. Sometimes it's not always possible to have the lowest on the scale, but the whole idea is you want the lowest possible that you can achieve, right? So this is a pretty good SWR for our transmitter being matched to the antenna through the transmission line or the feed line. Compare and contrast to the right-hand side what our meter tells us. This is another, maybe a different antenna or maybe some other issue causing the SWR to be high. How do we know the SWR is high according to this meter? Well, if we were to look at this needle, right, we'll see the reflected power. If we look at this needle, we'll see the forward power. So you'll see the forward power, if we were to read off, it's somewhere around 16 watts or so, or 16. And if we were to look at the reflected scale, you'll see it's all the way up here, right? So the needles now cross at a different point. So they cross all here. And if we look at this, this is an excess of 2, right? Maybe 2.1 or 2.2 or something like that. And that's a, higher SWR. So that's not as good as this SWR, where your reflected power, that wave that goes back down the line, is not as high. In this case here, you have a pretty high reflected, and it could go higher if you're match or you have a greater mismatch. So these are the SWR meter screenshots showing a pretty good or low SWR reading and a pretty higher or not so good SWR reading. Right. So we were saying that SWR are ratios. So on the left-hand side of this chart here, we have the various readings that you could read off of your SWR meter. When you put that SWR meter in your transmission line to read the SWR, or maybe your radio itself might have an SWR meter. And when you key your transmitter, you press your push to talk and you're transmitting and you're reading off that SWR, you have a very good SWR, 1.0 to 1. That's ideal, challenging to achieve. There are things that you can do to achieve it, but challenging to achieve. That's ideal. That means that you have no power loss and the output to the antenna is all 100%. That's what you're trying to aim for as a ham. Why? Because as a ham, we are all matchmakers. When we have that ideal or perfect match, we have maximum power transfer. That's what we're trying to do. But it's not as easy to achieve. And sometimes, we'll have less efficient SWR readings. We may have 1.4 to 1, which means a power loss of 2.7% and only 97.3 goes to the antenna, or rather is transmitted by the antenna output. But that's not too bad at all. And then we have where we begin to start to say we have a high SWR. And it's not unusual to have somewhat high SWR in your antenna system, right? But you want to minimize it as best as you can. That's one of the objectives, to get as low as you can go, to limbo down. So 2.0 to 1, on HF might be acceptable depending on the antenna that you have and so on. But you still have about 11% loss if your SWR meter is telling you 2.0 to 1, that ratio. That means you're only outputting 89% of the signal that you're transmitting. You're losing some of that, but still not so bad, And then you have higher, 3.0 to 1. That's when, okay, you're losing 25% of your output. Why would you want to do that? And you're only achieving 75%, but maybe that's okay enough, but you're still having a high SWR and you're going up in SWR. So when you're constructing your antenna, and you're connecting your antenna to your radio, you're aiming to tune that antenna down to the lowest possible SWR. And we have some graphs here that you can see that the problem with high SWR is that in addition to that, the loss in a transmission line is also increased, right? So just bear that in mind. We have some curves. We put it into your slide deck so you could always look at it later on. Good information to have. So SWR itself, apart from itself, reducing the power to the antenna, the amount that goes out, it also increases line loss on your transmission line. So you're kind of getting a double whammy there when you have a high SWR. You're already losing signal because of that reflective wave, your high SWR. But because of that, you're creating additional losses on your transmission line. So that's why a high SWR is not such a good thing. You want to reduce it to the minimum. All right, so we have been saying and talking about an SWR meter, and we've been saying that, you insert it in the transmission line or your feed line to read off the SWR. So this is a basic radio here that you're seeing here, your transceiver, you have your microphone and so on, and you have transmission line or your feed line that goes to the antenna. We have seen these representations before, but look what's different here. We have stuck in the middle here. We have connected using a little jumper cable or a patch cable, whatever you want to call it, and stuck it in the between here. And that's where your SWR meter will go, because you want to read your SWR. It will take the forward power and the reflected power and calculate for you your SWR. And that's what you want to know. You want the ideal 1.0 to 1 if possible, or lowest possible. But when you install an SWR meter, this is how it goes, right? It's a meter and it's going to read. Different types, as we'll see in a little while. But for the exam, we need to know a couple things about SWR and the SWR meter. And here are the points. SWR, or standing wave ratio, is a measure of how well a load is matched to a transmission line. And we say load, they're trying to tie you up here, but the load in this case is the antenna. So don't let them tie you up when you talk about a load. This is the antenna here, and we're referring to it as the load. So it's a measure of how well your antenna or load is matched to the transmission line and also your transceiver for that matter. All right, so this is an exam question that you need to know. Another exam question is that the reading on an SWR meter, that's this wonderful looking meter on your screen here, it indicates a perfect impedance match between the antenna and the feed line is 1 to 1 or 1.0 to 1. That's the ideal SWR. Difficult sometimes to achieve, but that's what we're all aiming for. Why? Because as hams, we are matchmakers. Another exam question, and it just plucks an arbitrary SWR reading. So I'm saying an SWR reading of 4 to 1 indicates an impedance mismatch, because that's a high SWR. So remember, if we were to go back to a couple of slides where we showed you the various SWR readings, 1.0 to 1, 2.0 to 1, 3.0 to 1, 4.0 to 1, as you go higher, you have greater losses, right? So you just need to bear that in mind, that an SWR reading of 4 to 1 indicates an impedance mismatch, right? Exam question. All right, let's continue with some more exam questions. So again, we have this diagram up to show your SWR meter in line, reading it for you. And we need to know that a benefit of a low SWR is reduced signal loss. That is also saying that you have maximum signal transfer. So you want a low SWR, as low as you can go. And another exam question, we need to know that the power lost in the feed line, that's this feed line here, also known as transmission line. Sometimes you will see it called coax, or different types of lines that you use, is converted into heat. So when you have a high SWR, that is where the losses go. They go into heat, right? Which again, not a very good thing. Why would you want to waste all of that power and transmission in losing it in heat, right? Not a good thing at all. So for the exam, power lost in a feed line, and it's also due to the high SWR, we put that in there, it's converted into heat. So that's how it's lost. Instead of the signal going wirelessly into the air for you, you're losing it in the transmission line. It's giving off heat. How is that a good thing? It's not. Also, another exam question. So of course, we talked about semiconductors and solid state equipment. So most of today's equipment is solid state. So most solid state transmitters, such as this one, will reduce output power as your SWR increases. So as the radio senses a higher SWR, it will say, you know what, I don't want to damage myself because I'm being detuned. My transmitter circuit is being detuned, and that means I'm going to generate a lot of heat. So to protect myself, modern transceivers, the solid state type, will look to reduce the output power. If it is detecting a mismatch along the line, it will try to do that and reduce the power output to protect itself. So we say that most solid state transmitters reduce the output power as SWR increases beyond a certain level. Why? To protect the output amplifier transistor. So we did say that your transceiver, your transmitter, has in its power output, or the PA or the power amplifier, transistors. Those are the things that increase the power to very high levels, to send it out to the antenna for you, while it's going to protect itself by reducing the output power if it sees a high SWR. So it's protecting itself, and you need to know that for the exam. All right, so there are a couple of things about the SWR meter that we need to know about. And it's like so many things. If you're getting a meter, you need to know what you're going to measure, and you need to get one that is appropriate to the power output. So you may have a transmitter that could do 100 watts out. So therefore, you might need an SWR meter that could handle, well, not exactly 100. You don't want to go exactly at what the output is. You might want to go something higher than that, right? Just to have a little bit of headroom. But you wouldn't put a 100 watt rated SWR meter if you have a 1000 watt power output transmitter, right? So you need to match your meter to make sure you wouldn't blow the meter by putting it into something that it's not built to accept. And that is actually the topic of the next exam question here in yellow. You'll see that when selecting an accessory SWR meter, again, they're trying to tie you up by using extra word, accessory SWR meter. That simply means it's an external SWR meter to the radio, because some radios, some transmitters, some transceivers will have a built-in SWR meter that you just press a button and you'll see it on the display here. But this is an external or an accessory SWR meter. So don't let these extra terms tie you up, you know. Accessory SWR meter, the following should be considered. First of all, it has to be rated for the band that you're going to be using. So the frequency as well as the power level. So you don't want to put a 100 watt rated SWR meter into a 1000 watt circuit here like this, right? So you need the frequency and the power level at which the measurements to be made. So you basically need to select that SWR meter carefully. You need to have that headroom so that you don't mash it up, all right? So there's also another meter or another instrument that you can use to measure standing wave ratio, right? Besides an SWR meter, and that is called a directional watt meter. And we have a little diagram of it here. And we will also show another picture to show how, you know, we put it in line and we can measure. This meter can measure SWR meter. How does it do it? Because it's a directional watt meter, it is able to measure the output in one direction, that's the transmit power, and it can also measure the reflected power along the transmission line. Because it's a directional watt meter, you actually just turn this knob here and turn it left or right, and it'll tell you the power going in this direction and the other direction. And remember, it's a ratio. So it's not as convenient as the SWR meter, because you still have to calculate it a little bit here. The SWR meter, you just read off SWR off the bat. This one, you have to get the forward power and the reflected power, and then, you know, you work out the ratio. But you can also use that, and that's an exam question. If you don't have an SWR meter, but you do have a directional watt meter, you can use it, and that's it. The exam question. Another instrument that can be used to determine SWR besides the SWR meter is a directional watt meter. This is what it looks like, and we'll show you it in a diagram shortly. Right, so this diagram here shows us using our directional watt meter. We just slip it in where we would have put the SWR meter, and then we measure the forward power, and then we measure the reverse power, and that's how we will get our SWR. So this is where we install it, and that's another exam question. An RF power meter or watt meter should be installed in a feed line between the transmitter and antenna. In other words, it's not going to do it by itself in free space. You have to put it in line. So yeah, that's a simple representation. You have your radio, you have your transmission line, and you have your antenna. But to measure, you need to stick this in the line, right? Usually they have a little jumper between the transmitter or the transceiver and the instrument, and another one from the instrument going to your antenna, which is your transmission line. So this is sometimes called a jumper. Some people will call it a patch cord, you know, different names people may call it, but it's like a little jumper of coaxial cable that goes between your radio and the instrument. So this is where it goes, and you need to know that for the exam. All right. So there's yet another instrument that we need to know as amateur radio operators. This is actually a very versatile type of instrument. It can do many things, and it's called an antenna analyzer, right? A little bit costly, but it's a good investment to have as an amateur radio operator, especially if you want to check the efficiency of your antenna. You're building antennas, you want to know if it's resonant. You're putting up the antenna, maybe it's up for a little while, you want to double check. And you can use this instrument without a radio. It connects directly to the antenna and will measure the antenna on the feed line and to see if it's matched, right? So this is the antenna analyzer, and you connect it to the feed line or the transmission line to the antenna. And it has its own little frequency generator. What it does, it generates a little frequency, just like your radio would. Send it down the line, see what the reflective is, and will even read out SWR, impedance. It does quite a lot of calculations inside of there. Tells you a lot about your line and antenna match, right? So this is an exam question. We need to know an antenna analyzer. This instrument here is used to determine if an antenna is resonant at the desired operating frequency. In other words, hams are matchmakers. We want to know if this antenna is resonant, if it's matched to the frequency that we intend to use it on. So the good thing about this, you don't need to use a radio. It's an instrument by itself. It can stand alone, and we connect it to the transmission line, and we get that. It's a very low power device, and it will tell us if it's matched. So very, very versatile, highly recommended instrument to acquire. And of course, like any other instrument, it can work on different bands. So you have ones that can do the HF bands, and some that can do HF plus VHF, and some can also do HF, VHF, and even UHF. Of course, the price increases as you go for additional band coverage. So you want to get the instrument that will work best for you. So let's look at the lineup of these instruments, right? So here they are. We have the SWR meter. This is the digital type. You have a nice, lovely digital display there. It'll tell you 1.0 to 1 or whatever. But there's an analog version. We're just showing that you have different types, right? You will read out the SWR here as well. You have the directional watt meter that we looked at a little while ago, and we have our antenna analyzer. So we just got sort of a little lineup here showing you the various instruments that amateur radio operators may use to measure this parameter that's so important called SWR. That tells you a lot about the efficiency of your system, the matching of the antenna to the transmission line, and the output of the transceiver. So as we said, hams are matchmakers, and these are the instruments that we use to determine that match. Okay, so let's do a couple more slides before we take our break. So an antenna tuner, remember we said hams are matchmakers. So what if our antenna is not properly matched to our radio? Well, we can use something called an antenna tuner, stick it in the circuit, and we can tune that antenna. Now, it'll be ideal to have an antenna that is already tuned for the frequency band that you're going to use. But sometimes you, as a ham, you will have an antenna that you want to use for multiple frequencies. So to achieve that match, you have an antenna tuner. And you can read this little bit on the slide deck when you get your slide deck to see what an antenna tuner is defined as. It tells you that it consists of an LC circuit. Well, if you remember from a couple sessions ago, L is an inductor, C is a capacitor. So you have capacitors and inductors in here, and you turn the knobs to adjust variable capacitors, variable inductors, and so on. And that's what an antenna tuner is. It helps to tune the circuit. All right, so this is what an antenna tuner for the HF band may look like. You have the knobs here that you turn on and so on, right? So it's just making it real. But let's see where it is installed. How do we install it as a ham when we're using an antenna tuner? All right, next slide up. All right, what do we have on this slide? Well, this is our ham shack. We have our equipment in our radio room. And what do we have? Well, this is a receptacle outlet. That's the wall outlet. And then you have plugged into it our power supply. We have to power it somehow. So in this case, it's an AC to DC power supply converter, adapter. It could easily be a battery that you're using. And we highly recommend for emergency communications that hams use batteries. But a power supply, a converter like this to use the AC line power is quite fine, right? So we connect it to our radio via a cable, DC power cable, and this is our transceiver or radio. We don't have a microphone connected, but keep things simple, this is our transceiver or transmitter, and we want to talk to someone, right? And we have our antenna on the right-hand side here. So we have a feed line or transmission line that goes to the antenna. We have been accustomed to that in our diagrams that we've been looking at. But look what we have just inserted, a component, an accessory into our transmission line or feed line. We recognize it as the antenna tuner from our previous slide. Why? Because this is our HF transceiver that operates on many bands. It might operate on the 20-meter band, the 40-meter band, the 80-meter band. And the antenna itself may be a multi-band antenna, but there may not be such a good match on some of the bands. So what do? Do I have multiple antennas that I connect to my radio? Some hams do. But I may want to just use one antenna, but I want to operate on all of the bands, right? So it may be resonant on a couple of the bands, but not so much on some. So I use my trusty antenna tuner and I tune it up for a good SWR. And I could use the SWR meter on the radio, or I could stick another SWR meter inside of here. Some antenna tuners, like this one, has an SWR meter on it. That's what that is on the dial right here. So we will tune our, use our antenna tuner to make sure we have a good match for the antenna to the transmission line and of course our radio. So this is where we place it, right? And this is an exam question that we have here. It says the major function of an antenna tuner, also called an antenna coupler, is that it matches the antenna system's impedance to the transceiver's output impedance. So remember, that's what we're trying to do. We want to try, it's a 50 ohm, just to let you know, 50 ohm impedance. The transmission line is 50 ohms. The HF antenna, I mean, we'd want it to be 50 ohms. Many antennas are not 50, and that's why we have to tune it or use an antenna tuner so that we get 50 ohms. So we have a nice match. And inside of here is where the match occurs. And we have a very nice, our tune circuit on the transceiver is lovely tuned, maximum output transmission. It will not clip, it will not back off the power for us once we are well matched. And then our antenna will radiate our signal to go as far as possible. Use the ionosphere and talk to another amateur radio operator around the world. That's what we're trying to do as amateur radio operators. So this is an exam question here. Again, for those who may have not been in the sessions where we mention it, once you see a bullet point in yellow, these are actual exam question components. All right, let's do one more slide before the break. Dummy load, probably two more slides, right? So dummy load, what's a dummy load? So we did say in a previous slide when we looked at the antenna, we said it's also called a load. So we can replace our antenna with this device here called a dummy load. Now, when we use this in place of an antenna, we will not really transmit very far, but the dummy load is an excellent match. It is 50 ohms. So once we connect our dummy load instead of an antenna and we transmit into it, that's a perfect match. Now, our signal will not go very far, admittedly, all right? But this is the dummy load. It's good to know what it looks like, right? We connect it, and on this next slide, we'll show exactly how we make the connection to the dummy load. But we need to know what the dummy load is used for the exam, and also the composition of the dummy load. So it's an important component that hams use for testing purposes, right? So for the exam, we need to know that the primary purpose of a dummy load is to prevent transmitting signals over the air when making tests. So remember we said it is not very efficient in terms of transmission. The signal will not go very far. It will go a little bit, but probably not beyond your house, for example, for sure, right? It's not going to go very far, maybe a little further, but it's certainly not going to be as efficient as a real antenna. But it will be perfectly matched to your radio, and hams use that for testing. Also, what does it consist of? Well, that's another exam question. A dummy load consists of a non-inductive resistor mounted on a heatsink. So let's dissect this point here. So this is our dummy load here. What does it consist of? Non-inductive. So remember when we talked about an inductor? So we're saying this is non-inductive. What do they mean by that? Now, if we throw our minds back, we may recall that an inductor, right? We use L for inductor, inductance. And what did we say an inductor was? Let's think about it for a moment. A coil of wire, right? So that's an inductor. So what they're trying to say here, that it's non-inductive. So there's no inductor, there's no coil of wire inside of there. Why is that? Because if we had a coil of wire, then that could make it resonant and detuned and all of that, right? So it needs to be non-inductive. It needs to be a resistor. So it's not the type of resistor that's made of a coil of wire, right? And it's mounted on a heatsink. Why it's mounted on a heatsink is because it's going to dissipate. If you're transmitting 50 watts or 100 watts into it, it needs to dissipate that power safely. So that's why you have this big heatsink here, because it's going to get pretty hot pretty quickly. So you need to have this heatsink to draw all of that heat and make sure it is safe and dissipated for the length of your transmission. So that's why dummy loads tend to have these heatsink fins on the side. So this is how it's constructed. It's non-inductive resistor mounted on a heatsink. And you need to know this for the exam. Let's do one more slide on dummy load and we'll take a break. All right, and this is just to show you how we use our dummy load, right? So we have our radio here connected to the power supply as before, but you'll notice that we replaced the antenna with the dummy load, and that's how we connect it. So we're doing some tests. We want to see if our radio is working well. Is it driving 50 watts, 100 watts? Of course, the dummy load needs to match the output power as well. So I wouldn't want to transmit 100 watt from this transmitter into a dummy load that is rated for 25 watts. No. I need to go 100 watts or more, right, to be on the conservative side. So this is how I'll connect it. I will put my microphone connected. I will transmit. I may speak into it. I may whistle or use a tone and generate. But the good thing about it is that this signal is not going to go very far. I will not cause harmful interference to anyone. I want to test my transceiver, see if it's transmitting. I want to check it out. I do so safely with the dummy load. So folks, let's take our little midway 2-minute break at this time. Get up, maybe have a glass of water, take a stretch, walk around a little bit, bathroom break, and will see you back in approximately 2 minutes time. All right. Yeah, good evening, Adish. Great to have you. So Norman, um, Norman asks, is there wattage that is recommended for SWR meter? I noticed the ranging from 100 watts to 300 watts. So I would answer that by saying just make sure that it covers the maximum transmitter power that you're going to connect it. That's my little rule of thumb. So if my radio is going to do maximum 100 watts or so, right? Need to cater a little headroom for the little peaks and so on. So yeah, I will go with a 300 watt. I could do that. I wouldn't go with one that's exactly 100 watt. I don't like to, have things that close. I always like to have a headroom. So my rule of thumb, just make sure it exceeds the maximum. So if you have a 1500 watt power amplifier, I may want one that could do, maybe 2.5 kilowatts. That's how I will look at it. But just make sure you have good headroom as well, and you don't transmit too long into if it's too close as well. So just be careful. You don't want to damage your instrument as well, right? Those things can be sensitive. So make sure you exceed the power output of your highest power transmitter. Make sure it matches the band as well. Thanks. Good question, Norman. Edward asks, the various meters are useful for measuring zero. Do these instruments need to be connected always, or is it just a momentary snapshot used to tune and then it can be disconnected? That's an excellent question. Many hams leave them in line right through, especially for HF. On VHF, hams tend to put it in, check it, and then remove it for VHF, UHF, those bands, right? I don't know too many hams that leave an SWR meter in for VHF and UHF. Some may not. You just want to check it and see if that it's okay. I know some that leave it and monitor it all the time as well. But remember, any instrument, anything that you put in line as well, you're introducing a little bit of loss also, so it depends. On HF, I think it's pretty normal to have an SWR meter in line because quite often it's part of an antenna tuner as well, right? So the antenna tuner is there usually in line. Radios also do have their inbuilt SWR meter. So if it's built in, some hams will say, I'll use that. They think that from that perspective, that's the most important, perhaps. So so that's a good question, Edward. I think it really depends on the ham, what they wish to do. If you want to monitor continuously, which may be a good idea. But if you think every little, ounce of juice is important and you think that instrument is somehow in a minuscule way taking up maybe the connectors in it, you have loss, perhaps you might take it out, right? But many hams do leave it in continuously as well. So, that's a good question there indeed. All right. All right, let's see if we can pick back up where we left off and see if we could cover the rest of the material this evening. So folks, we will be going a little bit beyond as we're trying to cover all of the material, right? So ask your indulgence for some extra time. All right, so I think this is where we stop. Let's continue now. We come to talk about modulation, right? But what is modulation? You'll hear that term, we're modulating, but what is that? What are we doing? So modulation is when we use our radio, we have our voice that goes into a microphone, and our radio will place that voice onto a carrier wave. Remember we said the radio is transmitting radio frequency. So it will generate a radio frequency, but the radio will take our voice and impose it upon the carrier wave, and then you get a modulated RF carrier wave. So for example, this might be what you might visualize the wave to look like, and it goes down the transmission line and leaves the antenna. So when we say modulating, our speech is conveyed on to the radio wave, and that's what gives it the information and the intelligence to go out there. And when it goes to the other side, the receiver will pull that wave out, that RF wave. It will strip off the carrier and look for the modulation or speech and reconstruct it. And that's how the person on the other end hears us, right? So that's what modulation is. And we have a little bit of a longer explanation here. We encourage you to read it on your own time as to what modulation is. All right, so we need to know about a couple different types of modulation. So we did say that, modulation is we're talking about voice, but it could also be digital modulation. As we'll see in a little while, we do connect computers to amateur radio equipment, and they let the computer do the talking, right? But typically we will be speaking voice, speech, a mode that's called phone. We'll speak and the radio will generate the carrier wave or the RF wave and impose our voice on it. But there are different ways that that voice could be imposed on the carrier signal. And those are called the various types of modulation. So one of them is amplitude modulation. So that takes the wave, right, the regular sine wave. So this is our carrier wave, nice and smooth like that. That's what is generated. Then we apply our voice to it. And look what it does in the case of amplitude modulation. It varies the amplitude. So this is the carrier wave as generated. We throw our voice onto it and look what happens here. It goes up and down. That's amplitude, height of the wave has been change, and that's what we mean by amplitude modulation. That's what our voice does to the signal. But that's not the only type of modulation. We have frequency modulation. So notice the signal, carrier signal, is very similar to what it's generated at, but notice the frequency is moving. We're shifting it, so it's compressing here and it's wider here. So instead of modulating the amplitude or the height of the wave here, we are modulating the space or the distance between the wave. So that's called frequency modulation. The frequency here is lower, the frequency here is higher. The frequency here is lower, the frequency here is higher. So we are modulating the frequency with our voice. Our voice is going and being superimposed on this carrier wave. So we're modulating it in a frequency or horizontal way. Whereas at the top here, amplitude modulation, we are changing it or modulating it in a vertical sort of way. So there are more than one ways to modulate a carrier signal. We're putting our voice onto that radio wave. So AM, amplitude modulation, FM, frequency modulation. And there's another type of modulation that we need to know about that's called phase modulation, or PM. So you have one phase, it switches the phase here. One phase switches the phase here. So phase modulation as well. That is how we encode our voice onto the radio wave in different protocols. And of course, on the other end, the receiver will also have to speak that protocol and be able to know it's an AM or an amplitude modulated signal to strip the voice out of the carrier by knowing it's AM, FM, phase modulation. That's why you need to match the modulation when you're receiving as well. You need to know what it's transmitting as the modulation, and you need to match the receive side with the same modulation. Because if you go and try to listen to an AM transmission in FM mode, well, you might hear a little bit of stuff, but it's the fidelity. You may not be able to make out what the person is saying. You might be able to know that there's a signal somebody is transmitting. So you need to know the mode or the modulation. AM, FM, PM, amplitude modulation, frequency modulation, phase modulation. All right, let's do some more graphs here to show the differences, right? So we did say that when we have our carrier wave, so in this case here, the carrier wave is on the top. So our radio is generating this frequency, right? That frequency there, notice the wavelength and so on. And then our voice is our modulation. So we speak and then we meld this onto the carrier wave and we end up with this. So we saw that a little before. So we amplitude modulate or vertically change or shift the height of the wave. That's AM. Again, frequency modulation. Well, we have our carrier signal actually here on this diagram, right? So there's our carrier. Notice the frequency being generated. Notice the wavelength and so on, right? So that's constant carrier being generated. Then we throw our voice. This is our voice here, our message. We speak, and then we throw that onto the carrier wave. But we modulate it frequency-wise. So we don't amplitude modulate it, we frequency modulate it. And that means we shift, we increase and decrease the frequency, and we end up with this. Notice we have a higher frequency here, a lower frequency here. A higher frequency here, a lower frequency. Higher frequency because the waves are closer together. Lower frequency because the wavelength or the wave is further apart, all of these areas here. So this is frequency modulation. And then we have phase modulation. We have our carrier wave on top of here, right? And then we have our voice. We superimpose our voice onto the carrier, and then we phase modulate. So these are the types of modulation. So different ways to show, and hopefully this is helpful that we understand these different types of modulations. Yet another little table to talk about the difference. I will leave this to participants to read on your own, right? I will just mention one thing about this chart. Both frequency modulation and phase modulation are under the category of what we call angle modulation. So you don't need to know that for the exam as such, but don't be too tied up when you see angle modulation. What that is, just know that frequency modulation and phase modulation are types of angle modulation. And they have the AM or the amplitude modulation. So this is just some references. We have quite a lot of advanced students, and some of you like to compare and contrast. So this is some extra information for you. All right. Okay. So I think we repeated this slide inadvertently, right? So let's go on to the next slide. So we need to talk about repeaters. We did show this graphic on a previous session, but there's something specifically we need to know about repeaters, right? We'll come into repeaters later on in the course, but we need to understand what a repeater is. So we'll just go over that very quickly for you because there's an exam question in relation to modulation. So what is a repeater? Well, I like to think of a repeater as a cell tower. So most of us may use cell phones and we'll have that in our hand. And we kind of know that cell phone, which really is a radio, it's really a two-way radio, is communicating with a tower, and that's what a repeater is, right? Except that for radio, we may not have as many towers. When you go around, you see cell towers all over the place. But radio repeaters tend to be on a high spot or high mountaintop, and you may just have that standalone, not as many. You'll have hundreds of cell sites, but you'll have a couple of repeater sites maybe. But a repeater site is you have a tall mountain or some building or something in height, and you have a repeater. And what that repeater does is that it listens for your transmission from your radio on one frequency, and then it rebroadcasts your transmission on another frequency, so that all other users around will hear. Even users that if you were to try to speak radio to radio, they would not normally hear you. There's this big mountain, so the radio signal will be blocked, but the repeater will hear your transmission and it will repeat it. But what we need to know for the exam is that for repeaters in the VHF and UHF spectrum, it typically uses FM or PM, which is frequency modulation or phase modulation. And that's it right here, the exam question. The type of modulation that is commonly used for VHF and UHF voice repeaters is FM or PM. And that's the exam question. And that's why we kind of sort of covered again what a repeater is, so that when you see the question, you'll know, okay, a VHF, UHF radio here, and you have a repeater. The modulation is generating the carrier wave and you're putting your voice onto it. It's either doing FM or PM, not AM, right? Okay, so we need to know what packet radio is. So let's talk about what packet radio is, and then we'll talk about the modulation that is used in packet radio. So what is packet radio? So packet radio is a form of digital communication, and we will repeat this several times. Anytime you hear digital communication in amateur radio, it will usually mean that you're connecting a computer to radio equipment. Instead of using your voice per se, it's a computer. Of course, we'll come to other definitions of digital modes, but for now, anytime you hear digital mode, think of a computer connected to your radio, and you may have an interface device between the computer and the radio. So packet radio is one of those digital modes that you'll send a computer signal through an interface. It's called a TNC, terminal node controller, to your to your radio transmitter, and your signal will go out the antenna to be received by another amateur radio operator who will receive the signal, demodulate it, send it to the interface, and then display on the screen the message, right? So that's what packet radio is about. And we just need to know for the exam that for packet radio, that the type of modulation that is used for VHF packet radio is FM or PM. Again, similar to for repeaters, right? So that's something that will come in the exam. You need to learn it. So you can read here what packet radio is. You have a little diagram to show you a ham using packet radio. All right, so we need to be very familiar, and hams are quite familiar with this mode of transmission or this modulation scheme called single sideband or SSB. So let us go into a little bit about what SSB is. What is single sideband? So remember we said we have our carrier wave and we'll modulate it and we'll have a transmission and so on, right? So we have an AM wave here. If we were to look at it, we're transmitting. But if we were to look to the diagram at the bottom here, we have our carrier here. And when we speak, remember amplitude modulation shifts it up and down? Well, to the left and to the right, we have our lower sideband and our upper sideband. So anytime we transmit an AM signal, you have the carrier, that's the fundamental frequency. And then as we speak, we shift the amplitude of it. So these are the frequencies to the left and to the right that are generated when we speak. So this is called the lower sideband and this is called the upper sideband. But with single sideband, what we do, instead of AM where you have the carrier and you have the upper side and the lower side, we actually remove the carrier and one of the sidebands, and we are just left with the other sidebands. It's a very nice technique. We filter it out. We take out the carrier, we take out the lower sideband, and we just send the upper sideband, right? So that is a technique in amateur radio. It's called single sideband. So when we remove the carrier here and remove the lower sideband, we are left with only the upper sideband. And you can do the opposite. You could remove the carrier and you can remove the upper sideband and you'll just be left with the lower sideband. And hams use both lower sideband and upper sideband type transmission. We don't really use AM that much, although you can. It's not very popular, right? And you'll see why in a little bit. So after we remove the carrier and we remove the lower sideband, we are just left with this here, the upper sideband. So that is a technique in amateur radio. So if you think about it, sideband is a form of amplitude modulation because you start with your amplitude, you start with your carrier and then you amplitude modulate it. And then now you pull the carrier away and you pull one sideband away, so you're just left with one sideband. So that's an exam question that single sideband or SSB is a form of amplitude modulation. Why is it? Because you start off with an amplitude modulated signal, but you remove the carrier and you remove one of the sidebands and you're left with just one sideband. So just notice for the exam what SSB is in relation to amplitude modulation. It's a form of amplitude modulation. All right. So there are a couple other things that we need to know about single sideband, and these are some of the advantages as well, right? It's advantageous. So again, we repeat this diagram here for you so you can see the AM signal and the fact that, well, it's represented the sideways here, and we strip off the carrier and the lower sideband and we're just left with the upper sideband, for example, right? Or what we call single sideband. Single sideband could be either upper sideband or lower sideband. It depends on which one you strip off. And hams, by the way, have a convention between lower sideband and upper sideband. When you're talking about using lower sideband, hams, by convention, use it for frequencies 10 megahertz and below. And for upper sideband, frequencies above 10 megahertz, right? So that's a bit of a convention for hams. But for the exam, we need to know that single sideband is often used for long distance weak signal contacts on VHF and UHF bands, right? So VHF and UHF, when we're doing long distance contacts, we will use single sideband as opposed to, let's say, FM and so on, right? So SSB is used for long distance or weak signal contacts on VHF and UHF bands. That's an exam question you need to learn. Also, we need to learn that upper sideband is what you will use for the 10 meter HF, VHF, and UHF single sideband communications, right? So I'll have a little diagram, next slide, that hopefully might help us remember where we will use upper sideband and lower sideband. I mentioned it here in blue, 10 megahertz and below, we use lower sideband, 10 megahertz and above, we use upper sideband. But remember, 10 megahertz is a particular meter band and so on. So we have a little trusty diagram that we have been using the last couple of sessions, and we have just added on LSB and USB. So next slide, you'll see it. But for the exam, we need to know USB or upper sideband is the sideband that you'll use, not lower sideband, for 10 meter HF, VHF, UHF single sideband communication, right? So 10 meter HF, VHF, and UHF. These three bands, right? You will use USB or upper sideband. 10 meter band or 10 meter HF band, the VHF band, and UHF. So we did a little diagram here that hopefully will illustrate that. So you may remember this where we show the amateur frequencies and what the wavelength is. So when we talk about the 10, let's say we were talking here about the 10 meter HF band. 10 meters here. 10 meters is 28.0002 to 29.700 megahertz, right? That's the 10 meter band. And we say we are using USB upper sideband, right? So what we have done here in blue is show that the frequencies from here to here, these rows here, are lower sideband. And the frequencies, all the others up above here, are usually USB. That's the convention. So once you can learn that 10 megahertz and below, or 30 meters and below, lower sideband, and everything above that, everything above 10 megahertz, or above 20 meters will be upper sideband. So we just kind of put this in. This may help you remember, where to use USB, where to use lower sideband. So you don't have lower sideband here and then upper sideband here and then lower sideband here and upper side. That's not the case. From here to here in the spectrum, 160 meter all the way to 30 meters, this is lower sideband. Everything else by convention will typically be upper sideband. Now, they have some little exceptions, but for now, just let's use that rule of thumb. And hopefully this diagram that we've been using, we have added on in this light blue color here to show and cross-reference where we use lower sideband and upper sideband. I'm hoping this helps. All right, so here's a slide that I will not go through in any kind of detail now, but we have a definition of bandwidth, because we have to deal with bandwidth. So I'll leave it to participants to read this slide about what bandwidth is, on your own time. Please do read it on. It will help understand some of the material that we're coming up with here, but we would not go through this at the moment. This is for your own reading pleasure. So bandwidth, what we need to know for the exam. So we have been talking about the various types of transmission: single sideband, amplitude modulation, frequency modulation, and some others, including Morse code. So this is a graphical representation of the bandwidth or the space occupied by the various modes. And some of them are more efficient than others. Some only take up a little bit of space in the spectrum. Some take up a little more space. Some take up even more. Some are spectrum hogs and take up plenty more. So you notice FM, how wide it could be. AM a bit, narrow. SSB a little bit narrow. And CW or Morse code, very narrow. So how we like to think of bandwidth is like a highway or a roadway. Imagine someone is driving on the road and they're occupying one lane on that highway or one lane on that road. They are occupying a certain amount of bandwidth. But imagine that someone is driving down the highway and they're occupying two lanes. Well, they're using more bandwidth, right? That might sound ridiculous. So in some countries, in the United States and others, you may have 10-lane highways, 12-lane highways, 8-lane highways. So imagine hypothetically, CW is someone occupying one lane on that highway. SSB is maybe somebody occupying a couple of lanes, and AM even more lanes, and FM, imagine somebody occupying all the lanes on the highway. Wow, right? You'll see a road hog, in this case, bandwidth hog, right? So bandwidth is the amount of space or spectrum that a particular modulation scheme occupies on the spectrum. And some take up a little bit of space, some take up a little more. And we as hams need to know exactly how much space, right? So CW or Morse code, but by the way, CW is short for continuous wave. But anytime you hear CW, think Morse code, right? It takes up 150 hertz of space, not very much. Single sideband, whether upper sideband or lower sideband, SSB, single sideband, either one, occupies 3000 hertz, right? Look at that, quite a bit more. AM, amplitude modulation, occupies twice that, 6000 hertz. And we have FM, frequency modulation, that could occupy anywhere between 5,000 and 15,000 depending on the FM mode used. So quite a bit. And we even have another one here that we need to know for amateur radio purposes called Fast Scan TV. Now, Fast Scan TV is just like regular broadcast television that you would have normally looked on your free-to-air TV. That's Fast Scan TV. But hams also do Fast Scan TV. But look at how much bandwidth it takes up. 6 megahertz, right? That's a lot of bandwidth, right? So CW 150 hertz, 3 kilohertz for SSB, 6 kilohertz for AM, 10 to 15 kilohertz for FM, Fast Scan TV, 6 megahertz. Why? Because that is carrying video, which requires a lot of space, a lot of information has to flow compared to these which will carry typically voice, and CW is just tones, you know, ditto, da, da, right? So the more information you have to carry, the more bandwidth you have to carry. But these are things we need to learn for the exam, and let's show you the exam questions in relation to the bandwidth of the various modulation schemes. All right, so here we go. For the exam, we need to know that a characteristic of single sideband compared to FM is that single sideband have a narrower bandwidth. Let's check that out. Let's dissect that. So this is our single sideband bandwidth here. See how kind of wide it is. It's relatively wide compared, if you compare it now to FM, which is even wider. So that's what we're saying here, that single sideband, which is this, is narrower than FM, which is all of this, right? We're seeing it visually here. This space here is narrower than all of this space. And that's all this first bullet point is saying here, that this is narrower than this. Single sideband narrower than FM. Need to know that for the exam. Now, the approximate bandwidth of a typical single sideband signal is 3 kilohertz, right? So you just need to learn that. You learn what CW occupies, SSB, AM, and FM, right? And also Fast Scan TV. You need to learn that for the exam. So SSB takes up 3,000 hertz, and as we did conversions, we should recognize that 3,000 hertz is 3 kilohertz. See where all of these prefixes and multipliers come in? So I need to learn those things so you don't get tied up, right? You can convert at will. It's at your fingertips. Next exam question, the approximate bandwidth of a VHF repeater FM voice signal is between 10 and 15 kilohertz. All right, so that's what we need to learn for the exam. And this is FM voice signal, right? Another thing that we need to learn for the exam is that a disadvantage of FM compared with single sideband is that only one signal can be received at a time, and it is used something called the capture effect. So when we are transmitting with single sideband, you can actually have 2 or more hams transmitting at the same time on the same space. I mean, you may have a heterodyning, you may hear some noise and so on, but you might actually hear both of them speak, right, in a way. But FM, if you use that mode, kind of the strongest person is who you will hear, right? And that effect is called the capture effect. And that's actually an exam question, that a disadvantage of FM is that only one can be received compared to single sideband. With FM, you're likely to hear the strongest. With single sideband, if 2 people are talking, you might hear both. Now, that is not what you would normally do, but this could be important in an emergency where you have people trying to get help, let's say in a disaster situation. Using single sideband, you will probably hear both of them, and you know that 2 people are talking and you need to help 2. Whereas on FM, whoever is the strongest is who you'll hear. You may not hear the other person at all. You may hear a little bit of a noise with it, but you wouldn't hear the voice at all due to the capture effect. So this is an exam question in yellow. Right, so we did say we were coming to Fast Scan TV. So think of Fast Scan TV just like your broadcast TV, free to air, that still exists in many places. Hams also broadcast that sort of television signal as well. Right, so yes, as hams, believe it or not, you can be a TV broadcaster in that sense, right? Not at the same frequencies that the broadcast TV stations will use. You have to use your own allocated amateur radio frequencies. But it's not only radio to speak and send a computer signal, but you can also broadcast video. Yes, you can. And we're just showing here, what a signal looks like for Fast Scan TV. And this is just a little color bar just to show it's a television signal video that you're dealing with. Here's what you need to learn for the exam. The amount of bandwidth, we mentioned it before, that hams, when we're using Fast Scan TVs, the approximate bandwidth of that signal is 6 megahertz. All right. And this diagram, if you look at it from start to finish, you see here 6 megahertz. So the width of that fast scan TV. So you have the chroma, the luma, and the audio here and all of that. But the total bandwidth occupied is 6 megahertz. Need to know that for the exam. And also, remember we said that it is similar to broadcast. It's not exactly the same, but for our purposes, we say that the amateur radio version of it, called the analog fast scan color TV signal, is a type of transmission indicated by the term NTSC. And some of you may recognize that NTSC is the type of signal that we use for free-to-air. NTSC, they have other standards like PAL and so on. But NTSC typically used in the United States, Trinidad and Tobago as well. Okay, so let's do a couple more slides. We need to know, we did mention CW or Morse code previously. CW means continuous wave. Read that as Morse code, and this is what Morse code signal looks like. We said it's dits and das. Some people think of it as dots and dashes, right? But dits and das, this is what it'll look like, the actual signal, did-it-da, right? And to do Morse code, making it real here, this is a Morse code keyer, what you call an electronic keyer or paddle, and it's connected to our transceiver. So we're not using voice, we're not speaking into the radio, we're just pressing these paddles to generate the tones of Morse code. And this is our transceiver or radio, and it's connected to an antenna, and it goes out the airwaves. And on the other hand, we'll hear the Morse code and listen to it and interpret it. All right, so Morse code, but there are a couple of things that we need to learn for the exam. CW is another name for Morse code transmission, right? So exam question, right? And by the way, we have a little table here of the various letters and numbers and the dits and the das or the dots and the dashes. This is the Morse code, right? Just FYI, don't need to learn it for the exam. And also another exam question they'll ask you, which is the narrowest bandwidth. So CW, as we know, is the narrowest bandwidth. How do we know that? Well, our trusty diagram here shows it, right? CW, remember we said it's only taking up one lane. Look how many lanes these other guys are taking up. Wide, a number of lanes. But CW, very narrow. So CW signal has the narrowest bandwidth. Look at them there, nice and thin and slim. All right. We also need to know the approximate bandwidth that is required for a CW signal. It's 150 hertz, right? So you need to learn that, 150. Also, we need to know what an electronic keyer is. So this is what the electronic keyer might look like. An electronic keyer is a device that assists in manual sending of Morse code. So we use our fingers, index finger, and thumb, and we press on these paddles here manually, and that's how we send Morse code, right? Right? So we need to learn these for the exam. All right, so again, we're just emphasizing here that anytime we talk in amateur radio about the phone mode, phone simply means that we're speaking or we are using voice. So we're speaking into a microphone, into the radio to talk. So that's phone. Come across it later on in the course when we say we're using phone, right? It's speech, or we are talking. As opposed to digital modes, we said it before, and this is our last slide, folks. So we have a couple of exam questions in relation to digital modes, but remember we said anytime you had digital modes, for our purposes for now, think of a computer connected to our radio. We have an interface here. Some radios interface directly to the computer. Some of them need an integrated device called a TNC or an interface to connect the computer to the radio. So digital modes, for now, simply means connecting a computer to the radio and let the computer do the talking. We type on the keyboard and it will generate some tones via the interface, send it to the radio, and it will modulate the carrier wave with those tones. And we are not speaking, but we are sending data across. And we need to know that digital modes, there are some examples here. Our next session, we'll get into them a bit more. And this is an exam question. These are examples of digital modes. Packet radio, which we kind of talked a bit about before. IEEE 802.11. Well, what is that? Well, that is simply wireless LAN or Wi-Fi. Yes, and hams do use Wi-Fi in that part of the band, right? So more on that You'll get pretty excited. Imagine taking a regular access point and using an amateur radio firmware, and you're running a higher power, higher output power, and using a little more spectrum that's available to the public in that industrial scientific medical band, the ISM band, right? So yes, hams can use IEEE 802.11, that Wi-Fi. And another mode that is called FT8, which we'll get into in our next session. But this is an exam question. What are the examples of? They'll give you a list, and it's actually all of them. All of these are examples of digital communication mode where you use a computer of sorts to communicate on amateur radio. Packet radio, IEEE 802.11, also known as Wi-Fi, and FT8. Alrighty, so let's quickly go to our question pool review, where we deal with all of the questions related to the theory that we have covered in this evening's class. So we can speed through that and come to the end of our session. So let's go. First question up. What is standing wave ratio, SWR? So again, hams are matchmakers. So we know SWR is a measure of how well a load is matched to a transmission line. Okay. Next question, what reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line? Well, we did say 1.0 to 1 or simply 1 to 1 is the perfect match. That's what as hams we are trying to aim for and we are trying to achieve. 1 to 1 SWR. Next question in the question pool. What does an SWR reading of 4 to 1 indicate? Well, that's an arbitrary SWR reading that they've pulled there, but we need to recognize that's a pretty high SWR. And remember what SWR is? Matching. Hams, we are matchmakers. So if it's high, the answer is an impedance mismatch, right? Pretty bad SWR, or not so good, I should say, SWR. Okay, next question. What is a benefit of a low SWR? Well, when we have low SWR, we don't have much losses, so we have reduced signal loss. That's a good thing. And low SWR, as low as you can go. Next question in the question pool. What happens to power lost in a feed line? So we did say that it offers heat, right? So that's the answer. Power loss in a feed line due to high SWR is converted into heat. All right. Why do most solid state transmitters reduce power, output power as SWR increases beyond a certain level? Right. So remember we said that modern day transceivers will detect the high SWR and back off the power. It will reduce it. It's doing so to make sure that it doesn't damage itself unnecessarily, right? So it's to protect the output amplifier transistors, those final transistors as we sometimes call them. We don't want them to get too hot and burn out. So they protect themselves by backing off the power, reducing the power to protect those transistors and save you some money and heartache. Okay, which of the following should be considered when selecting an accessory SWR meter? Remember we said an accessory SWR meter is an external SWR meter, not part of the radio. You stick it in line in the transmission line. But when you're selecting that, the frequency and power level at which the measurements will be made, that is what you need to consider. You don't want to have a below the power level meter. And of course, it has to be for the right frequency. Otherwise, it won't work at all, or it won't work well. Which instrument can be used to determine SWR? Well, we said there were a couple of them, such as the SWR meter, but there's also the directional watt meter that we saw that we can use, right? Look at the forward power, the reverse power, and then we calculate SWR. Where should an RF power meter be installed? Well, we showed it on a diagram. It's in the feed line between the transmitter and the antenna. Next question in the question pool. Which of the following is used to determine if an antenna is resonant at the desired operating frequency? So let's dissect this question a little bit. They're asking us, what are they asking us? Which of the following? So it's one of the meters that's listed here that we can use to do what? Determine if an antenna is resonant, meaning, remember hams are matchmakers, so we are looking for matchmaking or a good match, resonant at the operating frequency. And we learned that an antenna analyzer could be used just like, just connected to the antenna, and it will tell us if it's resonant on a particular frequency. Antenna analyzer. Lovely instrument. Next question in the question pool. What is the major function of an antenna tuner, also called an antenna coupler? Well, hams are matchmakers, so that's the answer. It matches the antenna system impedance to the transceiver's output impedance. So that's what an antenna tuner does. We showed you a diagram where it's installed and what it's used for. Next question in the question pool. What is the primary purpose of a dummy load? So it is to prevent transmitting signals over the air when making tests. So a dummy load, very good piece of equipment for making tests. You're transmitting, but it's not going over the air and causing interference, right? And what does a dummy load consist of? They're asking you, how is it constructed? You need to know it's non-inductive resistor that's used, and it's mounted on a heat sink to dissipate the heat. So that's the answer. Right. Next question in the question pool. Which type of modulation is commonly used for VHF and UHF voice repeaters? So we talked about repeaters, VHF and UHF, and we said that it's either frequency modulation or phase modulation, FM or PM, for VHF and UHF voice repeaters. Okay, next question in question pool. What type of modulation is commonly used for VHF packet radio transmissions? We said similarly, it's FM or PM, frequency modulation or phase modulation for VHF packet radio transmissions. Which of the following is a form of amplitude modulation? So remember, we drew the diagram and showed you, well, you had the carrier, we put our voice onto it, and it modulates, so it's amplitude modulation. But we said we can strip off the carrier, strip off one of the sidebands, and that is called single sideband. And single sideband is a form of amplitude modulation because it starts with AM or it starts with amplitude modulation, and we remove some components, we strip them off, and we are left with a single sideband. Remember, it could be upper sideband or lower sideband. All right. Which type of voice mode is often used for long distance weak signal contacts on the VHF and UHF bands? Well, we said we use single sideband to do that, SSB. Next question in the question pool. Which sideband is normally used for 10 meter HF, VHF, and UHF single sideband communications? So they're asking us, is it lower sideband, upper sideband, double sideband? We use upper sideband for 10 meter HF, VHF, and UHF. So everything above 10 megahertz, right? We are using upper sideband. Lower sideband is anything below 10 megahertz and below. That little diagram that we show will give you that idea. So it's USB or upper sideband for 10 meter HF, VHF, and UHF. What is a characteristic of single sideband compared to FM? We said, well, in terms of the bandwidth, single sideband signals have a lower bandwidth than FM, and that's the answer. Which is the I say again, what is the approximate bandwidth of a typical single sideband voice signal? So let's dissect this question. What are they asking us? What is the approximate bandwidth? So bandwidth will be either hertz, kilohertz, and so on, right? Of a typical single sideband. So SSB, according to our trusty chart, takes up 3 kilohertz. You need to learn that. Memorize it for the exam. What is the approximate bandwidth of a VHF repeater FM voice signal? So it's FM and the VHF band, and we said it's somewhere between 10 and 15 kilohertz. A lot of bandwidth FM signals occupied compared to some of the others. Which of the following is a disadvantage of FM compared with single sidebands? So remember, we talked about the capture effect on FM. You will only hear the strongest usually, but in single sideband, you can potentially hear more than one, So good feature in emergencies where you may have people trying to get help. We said that the disadvantage is that only one signal can be received at a time. Okay, next question in the question pool. What is the approximate bandwidth of an AM fast-scan TV transmission? So the approximate bandwidth, a lot of bandwidth. It's 6 megahertz wide, very, very wide. That's like you're driving down a 10-lane highway and you are driving on all 10 lanes. You're taking up all of them. Pretty wide bandwidth that you're taking up, right, for video. All right, what type of transmission is indicated by the term NTSC? Well, it's about equivalent to the amateur radio analog fast scan color television signals, right? So you simply need to learn that for the exam. Okay, what is CW? We said it's really continuous wave, but we know that to mean Morse code. Anytime you see CW, Morse code. It's another name for Morse code transmission. Next question, which of the following types of signal has the narrowest bandwidth? So remember that little trusty chart that we showed? CW was the skinniest, the most mager, thinnest, right? CW, narrowest bandwidth, okay? What is the approximate bandwidth required to transmit a CW signal? Just 150 hertz. Very slim, very trim. Next question, what is an electronic keyer? Well, we had a picture of it. It's a device that assists in manual sending of Morse code, right? We showed a paddle type. Okay. And we'll end with the last question. So we got into a bit of digital mode. We asked the question about digital modes. What is it? Well, you're connecting a computer. So which of the following is a digital mode? Well, we said packet radio is one, IEEE 802.11, also known as Wi-Fi is another, and FT8, which we'll come to in the subsequent session. So all of these choices are correct. All three are in fact digital communications modes. So as we look to wrap up this evening, please contact us if you have any questions. I think we have caught up with most of the questions that students have asked. We have one or two left, but please communicate if you have any questions, either via WhatsApp or via email. On your screen are the addresses. Get it in your slide deck. All right, so just a reminder, this link has been sent to you in your email. Recommended video. We'll continue recommended over the next couple of sessions. Remember, we are doing light touch theory, exam focus. So there are some things that we wouldn't be covering in the class too much, but it's very relevant in terms of amateur radio operation. So we have a video for you to take a look at that will give you some practical radio operating tips. Please consider having a look at that video. It's about an hour and a half as well, and very useful for further understanding. Just to let everyone know, the volunteer examiners have indicated that they will be scheduling exam session in Trinidad and Tobago just soon after we have completed the course. So somewhere around August or so, coming closer, we'll advise of the date. So something to work towards. Right? We'll provide further particulars as the couple of weeks go by. So folks, our next session will be Friday, the 23rd of June, 2023, our usual start time, 8:30 p.m. So thank you very much, everyone. Do have a good night, good rest, and see you in the next session. And we just want to wish Happy Father's Day over the weekend coming up to all fathers. Take good care, all, and good night.